Evaluate the limit with either L'Hopital's rule or previously learned methods. Okay, so to evaluate this limit, the first thing, of course, we want to do is, I'm saying plug in the limit value, but here we're approaching infinity, so we can't technically plug in infinity. But if I were to let the function x squared get larger and larger and larger, the result, or if I let x be larger and larger and larger, then the value of x squared gets larger and larger. So this thing is approaching infinity. So it's approaching infinity here. E to the negative x. If you think about the graph of e to the negative x, it is the same graph as e to the x, but it is flipped. And what happens is as x goes to infinity, the y values go to 0. So this is of the type infinity times 0. And the problem with that is it's not of the type 0 over 0 or infinity over infinity. So we can't directly apply L'Hopital's rule as is. However, we can manipulate this, and we could say that this is the same as the limit as x goes to infinity of x squared over e to the positive x. So if this is y equals e to the negative x, y equals e to the positive x, then looks like this, where it grows to infinity as x gets bigger, which means I now have something of the form infinity over infinity, and I can apply L'Hopital's rule. So using L'Hopital's rule, this becomes the limit as x goes to infinity of 2x over e to the x, because e to the x is its own derivative. And this is still of the form infinity over infinity, because a linear would grow to infinity. So I'll apply L'Hopital's rule again. And this is now the limit as x goes to infinity of 2 over e to the x. And now what's happening is I have this constant value, but the denominator is growing without bound. And so if the denominator of a fraction is growing without bound, but the numerator is not changing, then the value of that fraction is going to be pulled to 0.